In this video, I'm going to discuss the application of boundary conditions to Green's functions. We're going to continue working from Mathematics of Classical and Quantum Physics by Byron and Fuller, and look at the application of boundary conditions to a second order differential operator of one variable, and apply, say, the differential equation of x of t equals f of t. That's f naught x double prime plus f1 x prime plus f2 equals f of t. We want to solve that, assuming that we have two homogeneous solutions where L of x1 and L of x2 both equal 0. Or the general solution is the superposition of our two homogeneous solutions, added to that the convolution interval of our Green's function with our forcing function f of t, where f of t, they were integrating over all t prime. We found we're going to use the Wronskian form of our Green's function. So our Green's function are, again, a second superposition of homogeneous solutions, along with a heaviside theta weighted set of ratios of determinants, and where we have f naught being the highest order function. We're evaluated at t prime. So we're going to try to find the form of the Green's function for two different sets of boundary value conditions. First one is what's called a fixed point condition, where we have a given point that the value of x and the value of x prime is specified. We're also going to try a 2-point condition where we have the values of x at two different points, and I'm taking 0 and 1 as the boundaries of interest for that. I've done that in this case 0 and 1 because we have the Green's function solution for that condition for the differential operator that we're going to consider in this video, and we want to be able to compare results. We have those results from two different methods in the book for each of these conditions for the very simplest differential operator of second order. Specifically, if we have a differential operator of d squared dt squared. So that is x double prime equals f of t. We can easily construct homogeneous solutions for this. We can say x1 is 1, x2 is t. Take the second derivatives of either of these, we're going to end up with 0, so those both satisfy. Lx1 equals Lx2 equals 0. Now we want to find, first we're going to have to find the Green's function for this particular differential operator. So our Green's function, we have f naught of t is 1, x1 is 1, x1 prime is 0, so we only have, and we have x2 is t prime, and x2 prime is 1. So the denominator will be 1, and in the numerator we have 1, 1, t prime t. Let's write that out. So our Green's function our first x1 is 1 plus beta x2, which is t, plus theta t minus t prime times, we had 1, 1 t prime t divided by 1 over 1, 1, 0, and this was t prime. Not that that matters, but we don't really care what this term is, since only the diagonal of this particular determinant matters. Anyway, so that gives us, we have alpha plus beta t plus t minus t prime theta t minus t prime. So there's our g. Now, we're going to figure out how do we solve for the boundary value conditions. So let us plug in this g into our x of t and see what we have before, if we don't have any clue what our boundary value conditions are yet. So we have x of t equals a plus bt plus alpha plus beta t plus t minus t prime theta t minus t prime all times f of t prime dt prime. Integrating between overall space. So we have here 1, 2, 3, 4 variables that we need to find values for, and we really only have 2 known values to plug into this equation. So each of the values, each of the boundary value conditions will give us one equation. So we have, essentially, we have a problem with 2 equations, 4 unknowns. So we clearly need some alternate strategy to deal with how to find all of our terms. So we want to find solutions for the homogeneous and for the Green's function, so that the Green's function and so that the combination satisfies all the boundary value constraints. Sorry for the discontinuity. There was a recording glitch. So we're going to start with the single point conditions, and that is x of a equals x naught, and x prime evaluated a is at x naught bar. So our homogeneous solution is just x naught plus x naught bar t minus a. So at t equals a, this is killed, we're just left with x naught, and the derivative is just x naught bar. So this clearly satisfies the homogeneous, our homogeneous system is satisfied, and our full solution is x of t equals x naught plus x naught bar t minus a plus some alpha plus beta t plus t minus t prime beta t minus t prime all times f of t prime dt prime. So now we have 2 unknowns, alpha, beta, and we have 2 equations, one which is x of a and one for x prime of a. Now, if we want this, we want to satisfy the boundary value conditions for all f of t, then having inserted our homogeneous solution with boundary value conditions satisfied, it means that at the point of t equals a, we require this term to be 0. And we're going to see that that gets a little bit fuzzy according to whether or not we are above or below a. So if we're approaching from below or above. So if we introduce a causality constraint on f of t, so let's say that f of t equals 0 for all t less than a. That's a reasonable causality constraint. So only the contributions from a to infinity for this integral matter. And now if we look at exactly how is g of at prime and g of g prime at at prime, what are those values? G at at prime is alpha plus beta a plus a minus t prime, provided a minus t prime is greater than 0, and it is alpha plus beta a if a minus t prime is less than 0. So a minus t prime less than 0 means that t prime is greater than a. So this is in the region of our integration. So that is part of the domain of interest, whereas matching boundary value constraints for this section of the interval, which is t prime less than a, is not very interesting. So we want to match boundary value conditions for t prime greater than a, and really we are looking at t prime greater than equal to a. So if we do that, we have here alpha plus beta a equals 0. There's one equation. Now our derivative gives us another equation. So g prime at at prime is, our alphas will be, if we take derivatives, our alpha is killed, beta t becomes just beta, t gives us a 1 that is in the t minus t prime greater than 0 region. T minus t prime greater than 0 means that t prime is less than t. But when we have t prime less than t and t equals a, t prime less than a is not of interest. So our derivative is beta plus 1 from below, and beta for t prime greater than or equal to a. Here we have t prime less than a. So this is the constraint that we want to match. So we say beta equals 0, and alpha plus 0 times a equals 0. So alpha equals 0. Green's function is now fully specified for the fixed point boundary value conditions. So we say that g of t prime is just t minus t prime times theta of t minus t prime. There we go. That is our Green's function corrected for the boundary value conditions of x of a equals x naught and x prime valued at a equals x naught bar. Fixed point boundary value conditions, we've found the form of the Green's function. This is exactly the form that is given in the book, found by direct integration, which is possible for such an easy differential equation. But now we found the same result using the Wronskian with the caveat that we have to match boundary value conditions. So next we'll go on to the 2-point boundary value conditions, and that is where the original recording will resume. X of 0 equals 0, and x of 1, 0, x naught, and x1. So with 2-point conditions, let's see how the functional form of the Green's function varies. So our general Green's function is g of t prime equals alpha plus beta t plus t minus t prime, for t minus t prime greater than 0, and we have alpha plus beta t for t minus t prime less than 0. G of 0t prime is alpha minus t prime and alpha for greater and less than 0, and g of 1t prime is alpha plus beta plus 1 minus t prime and alpha plus beta. So this one applies to here we had 0 minus t prime greater than 0, 0 minus t prime less than 0, and here we had 1 minus t prime less than 0 and 1 minus t prime greater than 0. Now our Green's function, when we do this convolution, we're really going to be only caring about the convolution from 0 to 1. So that's t prime is in between 0 and 1. And so let's see, does that change our domain? So here, this point is t prime greater than 1, so we don't care about that. And here we have t prime less than 0. And here got t prime is less than 1. And finally, this is t prime is greater than 0. So t prime greater than 0 is one of our constraints. Oh, and I see what's going on here. That is backwards. So t prime 1 minus t prime greater than 0 is t prime is less than 1. So we have two constraints here that we care about that are all within the integration range 0 to 1 of t dt prime. So let's look at those two constraints. So one of those constraints means that alpha equals 0. And the second constraint means that beta plus 1 minus t prime equals 0. So beta equals t prime minus 1. We can now plug that in. So we get g tt prime equals 0 plus t prime minus 1 t plus t minus t prime for t minus t prime greater than 0, and then we have t prime minus 1 t for t minus t prime less than 0. Simplifying, that is t prime t minus t plus t minus t prime. There we go. And t prime t minus t. Okay, so t minus t prime greater than 0, t minus t prime less than 0. The final kind of notational sugar that we can use here is to write this all as t prime t minus t prime theta, or t minus t prime minus t theta of t prime minus t. And that is the form of the Green's function that we found in Byron and Fuller for this was for the x of 0 equals x naught, x of 1 equals x1 case. And just reminding ourselves, we had for the fixed point conditions where x of a equals x naught and x prime at a equals x naught bar, there we had the Green's function was t minus t prime theta t minus t prime. Wildly different functional form for our Green's function depending on the boundary type conditions. It's this is a topic that's been a little bit mysterious to me for a number of years, since my first attempt to incorrectly use Green's functions without application of the boundary value conditions, and it didn't go well, and I wasn't getting the right answers. And it's really important that the Green's function be modified appropriately for the boundary value conditions. We see here how to do that in this very simplest case where we were solving d squared x dt squared equals f of t. So we have one differential equation, a forced, almost a Laplacian style equation, a harmonic oscillator without the intrinsic frequency, and two different Green's functions, one that applies in the fixed point domain and one that applies in a single point domain. I hope that this has been useful to somebody, or will be, and that is it for today.